Explain each of the special features in red of each of the following graphs. For the first graph, the graph intersects or crosses or cuts the x-axis at this point and this point. So these two are called the x-intercepts. It crosses the y-axis at this point, so this is called the y-intercept. And so wherever the graph crosses the horizontal axis or the x-axis, we call it the x-intercept. And if it crosses the vertical axis or the y-axis, we call it the y-intercept. Since the graph passes the vertical line test, there should be at most one y-intercept, but there might be more than one x-intercept. The x-intercept is also known as the zeros of the function because at these 2 points, the function or y equals 0. As we observe or study the graph from the left to the right, we see that for the second graph, the function is increasing and then decreasing. At this point, there is a local maximum. Once it's past that local maximum, it is decreasing and then increasing. And so at this point, we have a local minimum. Then it is increasing, but then it keeps going up all the way. So there will be a singular point here. And also, the function is not defined at this point, so there will be no extreme values here. For the next graph, as we move from the left to the right, it looks like the graph is concave up and then it concaves down. Wherever it changes the concavity is where we have an inflection point. Similarly, the graph is concave down, just slightly concave down and then concave up. We have an inflection point. It is very subtle here that the graph is concave down on the left of this red dot and then it's concave up, and that is why we have an inflection point here. This is not an inflection point because on the left hand side of it the graph is concave down, and then on the right hand side the graph is also concave down. The graph does not change its concavity at this point, so this is not an inflection point. For the singular point, the graph is increasing without bound on the left hand side of this point, and on the right hand side is also increase without bound as well. And so we have what we call a vertical asymptote at this point. The equation of the vertical asymptote is x equals, and if this x value is a, then we have the vertical asymptote at x equals a. And for the last one, the end behavior is also known as the behavior at infinity when x goes to positive infinity or when x goes to negative infinity. This is the far left or far right. We see that at x go to the left forever, or x go to negative infinity, the limit of the function or the graph is approaching the horizontal axis or 0. The same thing on the right hand side. At x go all the way to the right, the graph is approaching the horizontal axis or 0. What this means is that we have a horizontal asymptote, and the equation of the horizontal asymptote is always y equals a number. And since the graph is approaching y equals 0, which is the horizontal axis, we say that we have a horizontal asymptote at y equals 0.